Hello everyone, it's calculation time. Dr. Dave. This is a lesson on electrolyte solutions and concentration expressions of electrolytes. So what we talk about is that when we put stuff into solution, and by stuff I mean drugs typically, when we put them into solutions or we put certain minerals in solution, they will do one of two things. They will remain intact or they might dissociate. So for something like glucose in the blood, it will remain intact. It won't dissociate into anything, but certain ions might dissociate. So in the body, we certainly have a lot of ions: potassium, sodium, calcium, magnesium, and we have anions as well. The thing that we need to worry about first is for these calculations is the valence. And the valence here is the total number of positive or negative charges on an electrolyte. So total number of positive or total number of negative. All right? So for example, if I say sodium chloride and I say, what's the valence of sodium chloride? You would know that sodium has one positive charge. Chloride has one negative charge. Therefore, the valence is one. If I said calcium carbonate, calcium, it's got two. Carbonate's got two negatives, right? Two anions. So the valence is two. Now, we use electrolytes to treat a lot of disturbances in the body. You'll see them in tablets, liquids, capsules, and a lot of times in parenteral products is why we're talking about it. So a lot of solutions that we give by parenteral route will have electrolytes in them. I'm going to show you something that will help you solve these problems, I think, in the easiest way and help you remember, especially years later when you go to do your boards. So most people think that this is almost impossible to do. But I am going to show you based on this little diagram how you can make these impossible possible. All right. So I'm going to draw something that's not going to look that much like it makes sense, but when we start to do the problems, it will make sense. This is how we draw this diagram. I do not give credit that I made this diagram. It was shown to me when I was in school. That's why I still remember it. So it was by some other professor, but we will show you what it was shown by. So the first thing you do is on top, you put milligrams. Then below that, so I'm going to put milligrams in a box right here. Then below that, you're going to add another box. And in that, you're going to put millimoles. Millimoles. And you're going to draw an arrow this way here. And you're going to draw another arrow this way here. And here's what this means. If I want to go from milligrams to millimoles, so milligrams to millimoles, which is this way right here, milligrams to millimoles, I'm going to divide by the molecular weight. So I'm going to divide by molecular weight. If I want to go the opposite way, if I want to go from millimoles to milligrams, I am going to multiply by the molecular weight. Okay, not bad so far, right? So if I told you you got 10 millimoles of something, how many milligrams is it? If you know the molecular weight of the compound, you can give me the milligrams or vice versa with milligrams to micrograms. Now, or milligrams to molecular weight. Now, next thing we're going to do is I'm going to draw an arrow this way. Put a box here. This one is going to be Milli-equivalents. MEQs, Milli-equivalents. And we're going to draw another one this way. So if I want to go from millimoles to milli-equivalents, if I want to go this way, I am going to multiply by the valence of the compound, the valence. If I want to go from milli-equivalents, if I want to go from milli-equivalents to millimoles, so if you're given milli-equivalents to millimoles, all these are going to be by divide. You're going to be dividing them. Over here, I'm going to draw another line and another box over here. This one is going to be milliosmoles. I have milliosmoles. If I'm going to go from millimoles to milliosmoles, I'm going to multiply by, this time, the number of species in solution. Species meaning the number of particles, number of things in solution. And if I want to go the opposite way, if I want to go this way from millimoles to from milliosmoles to millimoles, I would divide by the number of species. So here's how it works. If you want to go from milligrams to MEQs, you take the milligrams, you divide by molecular weight, get you millimoles. Then you take the valence, you multiply, and now you're over in MEQs. If you want to go from, let's say, milliosmoles to milligrams, I take milliosmoles, I divide by the number of species, I have millimoles. I multiply by molecular weight, and I've got milligrams. Now, that is a cheated system in terms of showing you how to do it, but I find that it connects and makes understanding of what MEQs are. MEQs are based on valence. It shows you milliosmoles. The osmolarity of a solution is based on number of species, and it puts it into a concrete form for us to utilize for some of these calculations. Excuse me. So let's look at, the first one is Milli-equivalents. So what is Milli-equivalents and how do we use that chart that I showed you? All right. The term Milli-equivalents is used very commonly in the electrolyte solutions that we deal with in pharmacy. It is a measure of the chemical activity of the electrolyte. And as we've seen in the picture, it's related to the ionic charge that it has, more notably the valence of the ion. So we need to know what the valence of these ions are. You can see the chart in the textbook to do it. It's important for us to know some basic ones. The rest we can always look up. So for electrolyte solutions, right, if we know the total number of cations in solution, as we've seen before, it will equal the total number of anions, right? This means that the milli-equivalents of cations will always equal the same milli-equivalents of the anions. Even further, it'll tell us the milli-equivalents of the compound. What do I mean? So let's take an example. 40 MEQs of KCl will be equivalent to 40 MEQs of K of potassium and 40 MEQs of the chloride. All right, so milli-equivalent. So it's all the same. 40 MEQs of the compound is still the same as 40 MEQs of the PT, and it's still 40 MEQs of the chloride. Let's do an example with some calculations here. How many milligrams of KCl are represented by 10 MEQs of KCl? So, how many milligrams of KCl is what we're looking for, and it says that are represented by 10 MEQs of KCl. So let's start with our chart. Our chart shows we got 10 MEQs. So if I go up here, if I've got 10 MEQs, so I'm starting here, 10 MEQs, and I want to get to millimoles, because ultimately I want to get to milligrams, right? I take the MEQs and I divide it by the valence. What's the valence of KCl? Well, potassium is positive 1, KCl anion negative, so the total valence is 1. It's a total number, positive or negative. Total number is 1. So I would take 10 and I would divide it by 1. What do I get? 10. So I now know that 10 MEQs, right? This is all for KCl. 10 MEQs of KCl equals 10 millimoles of KCl. 10 MEQs down there. Do that differently. 10 MEQs gives me 10 millimoles because I divided by the valence, divided by 1. Now I want to go from millimoles and I want to go to milligrams. How do I go from millimoles to milligrams? I multiply by the molecular weight, as you see here. Multiply by molecular weight, and we go from millimoles to milligrams. Take the molecular weight of the compound, which is given to me. So I'm going to say 10 times the molecular weight is 74.5. Molecular weights will always be given to you for us. You can look them up. And multiply that by 5, you got your answer of 745 milligrams. So 745 milligrams of KCl is equal to 10 millimoles, is equal to 10 MEQs of KCl. Another question. A solution contains 10 milligrams per 100 mLs of calcium ions. Express this concentration in terms of milliequivalents per liter. So milliequivalents per liter. Let's take the milligrams here and convert it to what we need is milliequivalent. So let's convert this to MEQs, right? How do I convert this to MEQs? Well, let's work in the reverse direction we did. We know that we go from 10 milligrams and we want to go from 10 milligrams up here down to milliequivalents there. So we need to first divide by molecular weight. So we take 10 milligrams and we divide by the molecular weight. The molecular weight, the molecular weight of the calcium ion is 40. So 10 divided by 40 is 0.25, and that's 0.25 what? Millimoles, right? That's what we get, our millimoles. Sorry, right here. All right. Now, the last thing we do is multiply by the molecular weight, and, we're going the other way. So I divided by molecular weight, and now I need to multiply by the valence and get over to MEQs. What's the valence of this one? The valence is 2, as you can see, right? The total number of positive and negative charges. So I'm going to multiply this by 2. And when I multiply that by 2, I get my 0.5, and that's 0.5 MEQs now. Now, it didn't answer my question. I just got step 1. This is now saying that I've got a 0.5 MEQs per 100 mLs of this solution, right? What's the milliequivalents per liter? Well, you've got 0.5 MEQs, right, per 100 mLs. How much do you have if you got 1,000 mLs? Right? So we would take our 0.5 times the 1,000, and we would obviously have our 5. So moving it over. So 5 MEQs per liter. Can you do this dimensional analysis? Sure, you can do dimensional analysis as well. I'm just breaking it down to show you the steps of how that works if you do it. You can put them all on a unit path and get it. All right. Next thing is millimoles. So we did milli-equivalents. Now let's look at millimoles. Millimoles is the concentration of electrolytes, right, expressed differently. And this is usually with species in solution. This isn't that much in pharmacy. Usually it's in laboratory values, but it is something that we do see. And since the mole, right, is the molecular weight of a substance in grams, 1 millimole is 1/1000th of a mole, which is why in my chart here, I have milligrams here and I have millimoles here. I could substitute the word grams here and put the word mole here, but here I'm putting milli and milli. And usually it's because we work with those numbers more often in milligrams than we do in grams in pharmacy. So that's why that picture is drawn that way. So how do we approach some of these questions? So here's a question. It says, how many millimoles of monobasic sodium phosphate monohydrate, that's a mouthful, are present in 100 grams of the substance? So 100 grams is what we're starting with, 100 grams of the monobasic sodium phosphate monohydrate. We want to get to our millimoles. So first thing is that we have to convert it to milligrams, and then we're going to divide by molecular weight. So 100 grams is equal to 100,000 milligrams. So we have milligrams. We divide milligrams by the molecular weight is 138. So if we take 100, and we divide it by 138, we get that 724.64, basically. 724.64. And this is the millimoles. Right? Millimoles. All right. And it's also abbreviated, as you see there, millimoles. So millimoles, abbreviation you can use. All right, look at another one. Got a patient receiving a slow intravenous solution. It contains 40 MEQs of potassium chloride in 1,000 mLs. After 12 hours, 720 mLs of the infusion has been infused. How many millimoles of a potassium chloride were administered? Who wants to know that? That's what I'd ask. So we can do this, right? We can use our chart and we can make this and break it down into something easy that we can show. All right. So ultimately, let's look at the question. What's it asking us? How many millimoles of potassium chloride were administered? So we're looking for millimoles, right? That's where we want to go to. Where's our starting point? It says the patient received a slow infusion. It contained 40 MEQs and 1,000 mLs. And after 12 hours, they got 720. So let's see how many MEQs of potassium they got. 40 MEQs of potassium, right, of KCl, was in 1,000 mLs. I think I got one extra zero in there, 1,000 mLs. If we administered 720 mLs, you got 40 divided by 1,000 times 720, 28.8 MEQs is what was administered to the patient. Now the question is, okay, how do we go from that milliequivalence to millimole? We were to take the MEQs from our chart, right? So we can use our chart. We have our MEQs and we want to go first to millimoles. So we want to go here to millimoles, and then we want to go down here, I should say this way, and down here to milliosmoles. So we're going to divide by valence, and then we're going to multiply by the number of species in solution. So let's see what we have here. So we are going to divide by divide by valence. The valence of potassium chloride, total number positive or negative, is 1. So this is going to be divided by 1, which is the valence, right? And now we've got 28.8 millimoles, right? And we want to go from millimoles down to milliosmoles. We multiply by the number of species in solution. I'm sorry, I'm reading that even wrong. It is the number of millimoles. That's our answer. Even easier. All right. So that was for millimoles. I apologize. I'm looking at milliosmoles instead of millimoles. So that was even easier. Okay. Now let's go to the next one. The next one says a liter of electrolyte solution contains 131 MEQs of sodium and 4 MEQs of calcium ion. Convert each of these values to millimoles per liter. Millimoles per liter. All right. So 131, we have 131 MEQs, right, of sodium, and we've got 131 MEQs of calcium. Oh, sorry, apologize. 4 MEQs. Not reading this one well. All right, 131 MEQs of sodium and 4 MEQs of calcium. How do we get our millimoles? So we take MEQs and we divide by our valence. So we divide by our valence. And I apologize earlier if I was thinking of millimoles, but here we're talking about going from milliequivalents to millimoles. I'll talk about milliosmoles in a second. All right. So we divide by the valence. What is the valence of sodium right here? Well, the valence is total number of positive and negative. Total number of positive is 1. I divide this by 1, and what do I get? Lo and behold, it's the same number. 131 millimoles is going to be equal to 131 million equivalents of sodium chloride. Here it's calcium, right? This is actually plus 2 I should have. So total number is 2 as the valence. So if I divide this by 2, 4 divided by 2 will be 2. This is 2 millimoles, right? Is what this one will be. So the answer is 131 or 2 for sodium. Or sorry, for calcium. Boy, I'm really having a hard time today. All right, apologize. Now we'll finally talk about millimoles, which is what I was trying to say earlier. So millimoles is the number of, or it's based upon, right? The number of particles, the number of species that are in solution, which is what we have for osmotic pressure. Remember we talked all about that osmotic pressure, number of particles in solution. That's what the milliosmoles is being used for. All right. And when we say the osmotic pressure in millimoles, all right, for intravenous solutions, so if somebody is saying to you that they're looking for what is the milliosmoles, but they're looking for it in terms of an expression of its osmolarity, it's going to be milliosmoles per liter. So if somebody says, what's the osmolarity? Osmolarity of something. This is the units they're looking for. Looking for milliosmoles per liter. Milliosmoles per liter. We know how to get milliosmoles. We know how we do liters. You can use the equation, but what we're looking for, which is important, is the number of species in solution. That's the number of ions that are generated by dissociation. And here we're going to assume complete dissociation relatively when we do it. So we know normal saline, 0.9%. It says express this concentration in milliosmoles per liter. So what's the osmolarity of normal saline? Well, let's start with something, right? We need to start with probably milligrams because that's our chart that we did. So I know that 0.9 grams of sodium chloride, right, is in 100 mLs, but I want to know per liter. So how many milligrams or grams ultimately that I'm giving here is going to be in 1,000 mLs, which is a liter, right? So this will be 9 grams. This means that there is 9 grams of sodium chloride, right, in a liter of normal saline. This is also saying 9,000 milligrams, right? All right. All right, so that gives us the milligrams, and now we know we can go from milligrams to millimoles by looking at our chart that we can easily see that we're going to divide by molecular weight and get to our millimoles. So if I take 9,000 and I divide by my molecular weight, so 9,000 and I divide by molecular weight, in our case molecular weight is 58.5, shows us there. So 9,000 divided by 58.5 gives us 100 and, oh, sorry. Yes. 153. It was that 153.86. I'm going to keep that on the calculator because what I would ultimately do now is that I'm going to take this number, right? So I'm going to take milligrams. I'm going to divide it by molecular weight, and then I'm going to multiply by the number of species. So this is just step 1. I'm going to multiply this by the number of species in solution. The number of species in solution for sodium chloride is sodium will dissociate into, or sodium chloride will dissociate into sodium chloride. So 2. Number of species is 2. So if I take the number I just got and I multiply that by 2, I get 307.69. All right, 307.69, or it's approximately 308. 308 milliosmoles per what? Per liter of solution, or per liter of that. Now, if you doubt that you did it right, you can also look at an IV bag. And here's an IV bag for sodium chloride. And notice here, right down in the, actually, let me get this highlighter here. If you notice right here, you'll see it says osmolarity. Ugh, that was the wrong one. It says osmolarity, and it gives you the osmolarity in milliosmoles per liter as 308. And that's what we just calculated. It says it was calculated that way. So you can determine it experimentally, or you can calculate it as we did. So that's the calculated value. So osmolarity, when somebody says that, they mean how many milliosmoles per liter. All right. Let's look at dextrose. If you've got 5 grams of dextrose hydrous, which is D-glucose monohydrate, it's got one little molecule of water there, it was dissolved in enough sterile water to get 100 mLs. What's the concentration of dextrose in milliosmoles per liter? All right. Ultimately, what we want is milliosmoles per liter, right? We're looking for the osmolarity of 5 grams of dextrose hydrous in 100 mLs. That's D5W, right? It's dextrose 5% water. So dextrose, even though we say dextrose 5%, it's dextrose hydrous. It's literally D-glucose monohydrate that is dissolved in there. So 5 grams of dextrose is 5,000 milligrams. That puts us on our chart now, so we can start doing it. 5,000 milligrams of dextrose, right? And I say dextrose, but I mean the D-glucose monohydrate. So 5,000 milligrams of that. If I divide that by its molecular weight, which is given to me, the molecular weight is 198.17. So if I take that 5,000 and I divide it by 198.17, I get 25.23 millimoles, right? The number of moles in milli, so millimoles. When I go from millimoles to milliosmoles, I'm going to multiply by the number of species that is in solution. So the number of species that's glucose, or this D-glucose is going to go into is 1. Why? Because it's not an electrolyte. So when you put it in a solution, it's not going to dissociate anything. So this times 1, right, is going to give me the same 25.23 milliosmoles. Now that's the amount of milliosmoles per 100 mLs, right? This says, what is it per liter? So if I was to take this number and multiply it by 1,000, right, because that's the number of mLs in a liter, right? So if I had this is the number that is, 25.23 milliosmoles, right? This is the amount per 100 mLs. I want 1,000 mLs. I'm going to get the same number moved over 1, 252. So 252.3, right? 308 is roughly what it's saying. Now, if you think you did that wrong, you can also look at that and look at an IV bag, and dextrose, you're going to see right there, you've got 252 milliosmoles per liter, and we just calculated what that was. Same thing that they did. All right. So for this types of calculations, it is, I think, in your interest to help look at this little diagram that I think is very helpful and get you through them very quickly and easily, and also shows you the difference in terms of the terminology and what there is associated with. If you would like a more formal definition, or you want to do it as doing it in ratios or in terms of proportions to what they are equal to, it's easily found in the text as well for deeper knowledge if you want that. All right. So once again, this is pharmaceutical calculations. It's the most important class because it is the only one that counts.